Welcome to Study Loop.
We have a system here in which we have two magnets, one here and one here, that are repelling each other. So there's a gap here, and we have a non-magnetic block up here that's compressing them together, and then they're in a non-magnetic tube. And so then what happens is we remove this block quickly, and then because there's now a repulsive force acting and this is no longer in equilibrium, it's going to accelerate up, and then it'll go up some, and then it will hit a maximum value and then come back, and then it will oscillate back and forth because there's no energy dissipation modeled in the system, or mechanical energy dissipation. So we know that this initial distance is 4 millimeters, and the initial velocity is 0. We're then given the acceleration, which is minus g plus k over x squared. So the force between these two magnets is proportional to 1 over x squared, and then we're given the proportionality constant k. So we can use our integration method, because this would be a very nasty differential equation to deal with. We can use our integration method to integrate from v naught to vb, some unknown, the velocity of this magnet B at some unknown time position. And we have introduced a dummy variable vb prime. And then we know the acceleration as a function of x, so we can integrate from x naught to some unknown position of the B magnet. We can then do these integrals, and we get 1/2 vb squared minus v naught squared, and then these turn into terms like 1 over x, so we get k times 1 over x naught minus 1 over xb, and then minus g times xb minus x naught. So we have x naught and v naught from here, and we know what k is. So this actually gives us an expression for the velocity of this magnet in terms of its displacement. So we're asked to figure out when the velocity is a maximum, and we can do that when by setting, we find x when the acceleration is 0, and so we do that, and we get that. So the acceleration is 0 when k over x, the maximum displacement squared, equals g, or so the maximum displacement is square root of k over g. We can then plug that into our expression for velocity, and we find that that is 0.167 meters per second. And we also asked for the maximum acceleration, and that occurs right when the magnets are the closest together, because that's when the force is maximum. And so the acceleration at 4 millimeters is 15.19 meters per second squared. And then we can also make a little plot here, because we have VB as a function of x. And again, if we look over here, we have squared here, so we have two roots. So one root will be this top half of this egg-shaped thing, and the other will be this bottom half. So what happens here is that we start off at v equals 0 and x equals 4 millimeters, and we rise up here. We have some positive acceleration, and we reach a maximum velocity of 0.16 meters per second. Then we start to our acceleration, it changes sign, and we start to slow down. And finally, we reach a maximum displacement, which is this value. And then we start to come back down, start to fall back down towards the other magnet. And now the acceleration starts to kick back in. The acceleration between caused by the force between the magnets starts to overcome that of gravity, and we start to increase our velocity, and we get back to where we started, and we keep cycling around this. And again, because there's no energy dissipation, we will just continue on around this forever, theoretically.